In this video, I'm going to go over a couple trigonometric integration problems. The first one is the integral of cosine to the fourth of x. So notice I've got my two-power reduction formulas right there. With these problems, there's always different ways to do them. So just because I do it in one way in this video doesn't mean that's the only way to do it. To me, this is the most natural way to go about doing this one. So what I'm going to do is actually just do a bunch of a bunch of side work down here. So instead of writing the integral sign all the way through, I'm just going to rewrite cosine to the fourth of x. It's my side work. So before I go and even try to do any changes with these formulas here, I'm going to write that as cosine squared x squared. And you should be okay with that because there's four of them being multiplied right there, so that's the same thing. And then what I can do is sub this in for this guy right here. So that is 1 plus cosine of 2x over 2 squared. From there, I'm going to square everything out. I'm going to square the 2 and actually put it out front of a set of parentheses, 1/4. You could do this in multiple different ways, but that's the way I'm going to do it here. And then I'll probably distribute it back in later. But to me, it's just easier to pull it out. And then when I FOIL this, right, I get 1 for the first term, that's this squared. Remember, if I have x plus 3 times x plus 3, that's x squared, these guys, and then I get a 3x there, and I get a 3x there plus 6x plus 9, right? So it's double this guy. So notice I got a 1 cosine x, and then I'll get another one of those. So I'll have 2 cosine of 2x. And then from there, I get cosine squared 2x. Like that. So next thing I'm going to do is simplify this guy. And I'm just going to leave the 1/4 out front right now because I just don't want to deal with it yet. I can apply it in later. So that is 1/4, open parentheses, I got a 1. I got a plus 2 cosine of 2x. And then let's see if we can get that. Yeah, we got the formula in there. So notice here I've got a 2x. If I have cosine of 1 squared, it's 1 plus cosine of 2. So this is my so I got to do 2, which means that I will get plus fraction bar 2, 1, 1 plus cosine. And then what goes in the here? Well, it's 2 times that. So it's 4x. Hopefully that makes sense. Then now I'm going to kind of reorganize everything. I'm going to deal with this 1/4 and move all these things around at the same time. So maybe just for the sake of showing all the work in this video, I'll leave the 1/4 out for now. So I get 1, and then I get plus 2 cosine of 2x. And then I get plus, so this is a 1 over a 2, so that's a half. And then this is a cosine of 4x over 2, so plus 1/2 cosine of 4x. Close. Now, I got a 1 and sorry, I got this 1 and a half, right? So that is 3/2. And I'm going to distribute this 1/4 in. So if I take 3/2, which is this, and multiply by 1/4, I get 3/8. And then the next thing, I got a 2 cosine 2x divided by 4, so 1/2 cosine of 2x. And then this guy just needs to get that 1/4 multiplied in, so I get plus 1, not 4/8 cosine of 4x. So that is all of the work that I did to rewrite this thing. You can see that, this is a lot of work, and I think that writing that integral and the dx over and over and over again, you're just going to lose track of things. So my suggestion is actually just to do all this side work, and then we'll just get rid of this. Oops, delete. And then, then you're going to write this, and I'm using a computer, so I can just copy it. I can paste it here, move it. So that integral over here is just equal to the integral of this dx. And now there's just some pretty simple chain or u sub, like reverse chain rule here. So what do I get? I get 3 over 8x. And then, all right, we are going from cosine up to a sine, integrating. So it's positive still. But I got to deal with that too. So I get plus 1 over 4 sine of 2x. And then the last thing I'm going to get is 1/8 divided by the 4. So that gives me plus 1 over 32 sine of 4x plus a constant. Hopefully you see how I can use that double angle, or sorry, the power reduction formula. I say double angle a lot, and what I mean power reduction. To me, they're sort of the same thing. But I use that power reduction to reduce this until I don't have to reduce it anymore. If this was cosine to the 6x, then you would probably have to do a little bit more work, and it would take more work to FOIL things and stuff like that. So let's do another. In order to get into the next one, I'm actually going to show you one that you should probably already know how to do. Say I had to do the integral of sine cubed x. This one's easier than the one that we just did because this power is odd. I don't have to use any double angle formulas or power reduction formulas. Instead, I can just separate these out and do some stuff with the Pythagorean identity. The strategy is to leave one sign and then take the rest of them. So that leaves me with sine squared here when I multiply them out. Then that sine squared gets replaced with a cosine stuff, right? How do I figure out what stuff? Well, you should know the Pythagorean identity. You can solve for sine squared. I get 1 minus cosine squared. That goes here. And then I get a sine x. And then I just do some u work, blah, 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 blah. I get to here, and I get my answer. You should be totally comfortable with this. And I'm going to show you how to do this when we have secants and tangents for the next one. So the first thing that I want to talk about is what the identity is that involves secants and tangents. And I'm going to show you just how to get to it so you don't have to memorize it, because I don't really like memorizing things. You should know that we can get the Pythagorean identity by drawing a triangle. I'm going to use a theta. You could use an x there. Writing the opposite, writing the adjacent, writing the hypotenuse, as long as it's a right triangle. And what I can do is, I'm just going to let that be O, let that be A, let that be H, like you do with SOHCAHTOA. And I know that O squared plus A squared is equal to H squared. Now, you should be familiar with the fact that I can divide everything here by H squared, and that gives me the Pythagorean identity that's listed here. I can divide by things other than H squared and get different identities. For example, if I divided, well, say I wanted something that had tangents in it, right? I know that tangent of theta is TOA, opposite over adjacent. So notice I got an O squared, I got an A squared, and H squared. If I divide by A squared everywhere, then I get O squared over A squared and H squared over A squared. So really, this is O over A squared plus 1 is equal to H over A squared. I prefer to just work this out quickly. I don't draw a triangle. I just kind of like work it out quickly, whether it's on paper or in my head, instead of trying to memorize these things. And what's that give me? Well, I got tangent of theta plus 1, or sorry, tan squared theta plus 1 is equal to secant squared theta. And that is actually another, there are more than one Pythagorean identities. I think we typically think of this one, right? But this is also a Pythagorean identity. And why is it a Pythagorean identity? Because it comes from the Pythagorean theorem. So let me show you now how we can use this to do some other integrals that were otherwise not doable before this point. I'm actually just going to pick this up in another video. So you can see how to use this in the next video that I will publish.